Dear students, welcome to my new lecture. I am Rokhshana Parvin, lecturer, Department of Civil Engineering, All University of Bangladesh. This lecture content will cover seepage pressure and equation of seepage pressure, upward flow, quick condition, which is also known as quicksand, mathematical problems on seepage pressure and quick condition. Seepage is a process in which a liquid flows slowly out of a hole or through something. In soil, seepage is the flow of liquid into the soil. When precipitation occurs, some of the raindrops fall into the branches of the tree, which is known as interception. The most of the raindrops flow over surface, which is known as surface runoff, and during this time, some water enters into the soil by means of infiltration and percolation through the voids of the soil, and finally reached into river or groundwater. This movement of water into the soil is known as seepage. Seepage pressure. By virtue of viscous friction exerted on water flowing through soil pores, an energy transfer is effected between the water and the soil. The force corresponding to the energy transfer is called seepage force or seepage pressure. Thus, seepage pressure is the pressure exerted by water on the soil through which it percolates. So we can say, seepage pressure is the force or pressure of water into the soil. Equation of seepage pressure. If H is the hydraulic head or the head loss due to frictional drag of water flowing through a soil mass of thickness Z, the seepage pressure PS is given by PS equal to gamma W into H. We know water pressure P equal to gamma H. To convert H into hydraulic gradient I, Z has been divided and multiplied with the equation so that the value remains same. If H by Z equal to hydraulic gradient I, so we can write PS equal to IZ gamma W, where Z equal to length over which the head H is lost, I equal to hydraulic gradient equal to H by Z. If seepage force is J and the cross-sectional area of the soil is A, we can write seepage force equal to pressure into area, or J equal to PS into A. Replacing the value of PS from equation 1, we get J equal to IZ gamma W A. The seepage force per unit volume is given by J is seepage force divided by volume. Here, seepage force is IZ gamma W A, volume is ZA. And finally we get J equal to I gamma W. Remember that the seepage force always acts in the direction of flow. Upward flow, quick condition. When a flow takes place in an upward direction, the seepage pressure also acts in the upward direction and the effective pressure is reduced. When seepage pressure and submerged weight of the soil becomes equal, the effective pressure will be zero. In such a case, a cohesionless soil loses its shear strength and the soil particles have a tendency to move up in the direction of flow. This phenomenon of lifting of soil particles is called quick condition, boiling condition, or quicksand. When quicksand develops, the soil will be like this, as bubbling from the ground. As in quick condition, upward water pressure and submerged weight of soil become equal. So, sand particles will have no shear or bond strength and will not be able to carry any load. Equation of seepage pressure at critical hydraulic gradient and at quick condition. When seepage pressure and submerged weight of the soil becomes equal, the effective pressure will be zero. Thus, during the quick condition, effective pressure sigma prime equal to pressure of submerged soil minus seepage pressure. And in quick condition, effective pressure sigma prime equal to 0. So, sigma prime equal to Z gamma prime minus Ps equal to 0. As Ps equal to Iz gamma W. So, we can write Iz gamma W equal to Z gamma prime. Finally, we can write I equal to Ic equal to gamma prime divided by gamma W equal to G minus 1 divided by 1 plus E. The hydraulic gradient at such a critical state is called the critical hydraulic gradient. For loose deposits of sand or silt, if void ratio E is taken 0.67 and G as 2.67, the critical hydraulic gradient will be unity, and it has proved from the following equation. We know critical hydraulic gradient Ic equal to G minus 1 divided by 1 plus E. Here G equal to 2.67 and E equal to 0.67. Finally, we get critical hydraulic gradient Ic equal to 1. Quicksand is not a type of sand, but a flow condition occurring within a cohesionless soil when its effective pressure is reduced to 0 due to upward flow condition. Here is a problem. Let's read the question first. A coarse-grained soil has a void ratio of 0.78 and specific gravity as 2.67. That means E equal to 0.78 and G equal to 2.67. Calculate the critical gradient at which quicksand condition will occur. That means we have to calculate Ic. We know critical hydraulic gradient Ic equal to G minus 1 divided by 1 plus E. Here from question, void ratio E equal to 0.78. Specific gravity G equal to 2.67. Finally, after calculation, we get Ic equal to 0.94. This problem is related to seepage pressure. First, we will read the question. Water is flowing at the rate of 0.05 milliliter per second in an upward direction through a fine sand sample, whose coefficient of permeability is 2 into 10 to the power minus 3 centimeter per second. That means Q equal to 0.05 milliliter per second and K equal to 2 into 10 to the power minus 3 centimeter per second. The sample thickness is 12 centimeter and cross-sectional area is 50 centimeter square. That means Z equal to 12 centimeter and A equal to 50 centimeter square. Find the effective pressure at the middle and bottom sections of the sample if the unit weight of sand is 19.4 kilonewton per meter cube. So we have to calculate effective pressure at the middle, that means when Z equal to 6 centimeter, and at the bottom, that means when Z equal to 12 centimeter. Here given in question, flow rate Q equal to 0.05 milliliter per second equal to 0.05 centimeter cube per second. Coefficient of permeability K equal to 2 into 10 to the power minus 3 centimeter per second. Cross-sectional area A equal to 50 centimeter square. Unit weight of sand gamma S equal to 19.4 kilonewton per meter cube. We know unit weight of water gamma W equal to 9.81 kilonewton per meter cube. Effective unit weight of sand gamma prime equal to unit weight of sand minus unit weight of water equal to gamma S minus gamma W equal to 9.59 kilonewton per meter cube. Again we know from Darcy's law Q equal to KIA. From here we can find I equal to Q by KA equal to 0.5. Again sample thickness Z1 equal to 12 centimeter and Z2 equal to 6 centimeter. We know for upward flow of water the effective pressure is given by sigma prime equal to Z gamma prime minus Iz gamma W. So effective pressure at bottom, sigma prime equal to 0.562 kilonewton per meter square, and at middle, sigma prime equal to 0.281 kilonewton per meter square, as all values are given. And this is the end of our today's lecture. Thank you everyone.